Edit distance algorithm, or Levenshtein distance. The edit distance algorithm measures the minimum number of single character edits required to transform one string into another. Often it is performed with a dynamic programming approach using tabulation for efficient computation. It has a time complexity of O of m times n, where m and n are the length of the source and target strings. Let's see an example. We have a source string that is AB, and we want to transform it into our target that is AB as well. Our goal will be to compute how many changes or edits we need to perform to make this transformation. Here is the section of the pseudocode, so you can see we only make character comparisons as the current source character is equal to the target. We just move forward. Then we need zero edit operations in this case. Let's see another example. In this case, our source string is empty and our target string is cut. Here is the pseudocode again. As an empty character doesn't match the target, we need to perform one insert char operation per each of our target characters in the string. So we need 3 edit operations in total: C, U, and T. Now let's see a more complex example. We will transform the cat string into cut. Again, we want to count down how many edits we need to perform to make this transformation, but this time we will use the tabulation method, a dynamic programming approach. Here is our main table. Our source string will be placed in the column axis, where each character will be one column, while our target string will be placed in the row axis. You can think that each of these cells in this table is in fact a subproblem to be solved. The resolution of all the subproblems will help us to reach our final goal. We will also consider a base case in which our source string is an empty character and our target character is also an empty string. This is necessary to initialize the first set of values to proceed with the algorithm itself. We will fill our table in with the following permitted operations, which might be performed on each of the cells or on main table. Insert, which will have a cost of 1, delete, which has a cost of 1 as well, and replace, that can cost 1 if the characters are different, or 0 if they are the same character. First, we will fill out our first row, which is the base case. In the first cell, we consider the cost of editing an empty character from the source into an empty character in our target. In the first cell, both character source and target are identical, thus our total cost is 0. Next, in the row is the conversion of C into an empty string. This requires 1 delete operation. The next cell in the row considers CA source characters to be transformed into empty string, which requires 2 deletions. And the last cell in the row considers the character CAT to be transformed into an empty string, which requires 3 deletions as edit operations. We keep going with our base case across the first column. This time we are having as a source an empty string. The first target in the column 1 is the letter C. This requires only 1 character insertion from our empty column source. Likewise, the next cell in the column requires 2 insertions, C and U, and the last cell, 3, to form the string CUT. Once we have filled our base case, we can start filling the rest of the table. To help us see how to fill it in, we will have here 2 helping tables, one with the key and another one with the cost. The first cell is the replacement of C by C. Because both are the same letters, this replacement has a value of 0, plus the previous minimum value cell, which is 0 as well. This gives us a total of 0 in this case. Next cell in the same row is A against C. this replacement has a value of 1. Because A is not equal to C, plus the previous minimum value of 0 is a total of 1. The last in this row is the cell T against C. Again, this addition has a value of 1, since these are not the same letters, plus the minimum cell value, which is 1 in this case, to give us a total of 2. We can start now with the following row, and you can see the minimum cost here that comes from the previous cell is 0, plus the cost of the insertion, which is 1. I hope you can see the pattern now. I will keep quiet so you can try to predict the next filling by yourself. Here is the pseudocode. The key sections of the code are highlighted in yellow. We use 2 for loops to iterate on each of the strings and compare character by character. The principal part of the code is performed by the last red section that is activated if both characters are different. The algorithm will take the minimum value with regard to the value of the 3 neighbor cells, which at time represent also one of the 3 possible edit actions in our key table. That's all. Thank you for watching.